Hi, my name is Thomas Bzik. I'll be talking today on a variety of detection limit issues. The talk is called Detecting the Detection Limit, sort of like how do we define these things, how useful are they, and what can we realistically do with them. I serve as ASTM E11 Quality and Statistics Chair, and this talk was originally given as the keynote address in this ASTM Symposium for Detection Limits in 2018. A series of talks from that symposium were presented at PitCon in 2019 in the detection limits in environmental and analytical chemistry. It resulted in a book of papers. A fair number of us who gave talks at the symposium published papers in the ASTM STP 1618, Detection Limits in Air Quality and Environmental Measurements. And that was edited by Mike Versum, who was the ringleader of both the 2018 and 2016 detection limit conferences at ASTM, as well as the PitCon session in 2019. So detection limits have proven themselves to be a very worthy opponent to develop standard practices for them. And they remain highly controversial in practice, despite decades, perhaps even beginning to, not quite a century of effort, but starting to approach that. And the inability to obtain broadly accepted detection limit definitions is truly indicative of our collective failure in that we're not approaching the problem in the most appropriate manner. So our journey today in today's talk is we're trying to improve our chances of developing successful detection limit standards. This talk was given in the context of a conference of where the objective was to, what do we need to do to develop a more widely accepted standard practice. But realistically, in order to improve our chances, we have to do a critical examination of detection limit concepts and constructs. So in terms of where we're going today, we're going to take a broad view of the swamp. It's a mathematical and statistical and vested interest swamp that we look at. We're going to see that there's lots of sloppy statistical practices to go around. We're going to see that there are actually quite a few different detection limit concepts. We're going to take an examination of how important calibration is to detection limits and that it's often underappreciated. We're going to examine how much statistical uncertainty is really in detection limits. We're going to look at what are some of the ways we use detection limits, what are some of the data reporting practices and the impact of choosing to either detection limit sensor data or not. Talk about the best way one might approach building a detection limit standard, and then we'll summarize our effort of the day. So part of the reason that detection limit standards that are broadly accepted have remained elusive is that there are quite a few participants with different vested interests. Analytical chemists, their focus tends to be more analytical science or perhaps the business pressures of the company they work for. Statisticians, often involved, and they bring statistical theory, but many times they don't also bring analytical process knowledge along with the statistical models. The regulators, they're serving regulatory and political needs. They frequently have less deep statistical knowledge. The instrument manufacturers, they're interested primarily in selling their instruments, and they want to be able to claim very low detection limits because that's of commercial value. And contract laboratories are very much in the same boat. They're selling measurement services, and they want to be able to claim that they can achieve very low detection limits. So to develop a detection limit, we face a exquisite mix of science, misapplication of science, all sorts of business and regulatory concerns and pressures, political pressures, and how we actually simultaneously serve all these constraints in a mathematical statistical construct is very much a non-trivial task. I had developed a detection limit standard in semi-standards in the 1990s myself, and an interesting quote from my co-chair was that, Tom, my company sends me here to make sure that nothing happens, that nothing comes out of this effort. Now, the individual did not take that philosophy, thankfully, because he knew he wasn't being watched at the standards meetings, but those were literally the instructions that were provided. Detection limits are controversial because ultimately money is involved, business is involved with these. So these things are incomplete generalizations, but they give us a perspective that we have conflicting interests. So how are specifications or things like detection limits, how are they often set? They're often set without the participation of the analytical scientist. And in a broader context, without the participation of those who are being regulated by whatever the specifications or the limits are. And generally, limits are set by those who are not necessarily knowledgeable about what limits are physically achievable or practically achievable, but sort of the idea, well, if they're bad enough, you'll complain, and we might listen at that point or we might not. So basically, often limits, even detection limits, whatever regulatory limits themselves are set without understanding sometimes what is analytically feasible or feasible at a reasonable cost. The customer is not the analytical scientist. Again, these are incomplete generalizations. So in practice, this applies to more than detection limits. I'm a professional statistician by training, but sloppy statistical practices are very prevalent out there, and we'll look at the ways that they haunt detection limit definitions. There's too much assumption of a normal distribution. There's a strong assumption of what's called homogeneity of variance, that no matter what level I measure, the variability is the same. That happens very infrequently with trace contamination measurement. Generally, everyone prefers computational simplicity over a more reliable method. We frequently do not build statistical methods to explicitly match the goals. What is the detection limit supposed to accomplish? And we often the statistics are not built to match the real characteristics of the data. And this is part of the reason that detection limits remain controversial. There's often a mismatch between practice and what the data says practice should be. And very often, in the name of simplicity, I would say, individuals will try to force a detection limit problem into a known statistical methodology rather than finding a methodology that fits their data. So the goals of detection limit building are more than just getting a good standard or standard practice. And what I would say in terms of simplistic statistical methods, many of them do not survive their first encounter with trace contamination data. So even the definitions of detection limits, we're going to see that there are many. I'll mention 20 or 30, but well, there are many more than I mentioned. And the terminology is used inconsistently as well. In the past, a well-known scientist from NIST, Lloyd Curry, he made some serious attempts to resolve terminology. What I would tell you is some have listened, some have not. We'll talk a lot more about some of the Lloyd's ideas as we go through the presentation. Detection limit language is loose, is the only way I can describe it. And my usage of just the idea of the concept detection limit will be purposefully loose because I want to talk about quantitation limits. I want to talk about method detection limits. I want to talk about, practical limits. I want to talk about them as sort of like a family of concepts. And perhaps we even need a detection limit terminology standard. Lloyd tried to write one, but even that remains controversial. And a little pun on words, we're going to try to figure out what the L is a detection limit. So, why do we even have a detection limit concept? Well, we know that our measurement processes are subject to variability, and we have this sort of terrible limit as we approach zero, and our measurement system reliability is, in a relative sense, frequently deteriorating as we approach zero. And we have analytical systems where we can detect something, the instrument provides a measurement, even when something is not present itself. Materials may not even be detected, even when they're present at some level. And these lines with the two, stars or asterisk stars at the end, think of it as they're going to be sort of two classes of detection limit concepts that are people tend to fight over which one to use. Do I try to prevent false detects, sort of the first one, materials can be detected when none are present? Or am I more concerned about what's the level at which I can say with some level of reliability that I'm almost guaranteed to get a signal? So that second one is what Curie liked. The first one is perhaps more common in usage, but both concepts have a utility, but frequently there's not agreement which one to use. And we know that when we have trace specifications, regulatory specifications, there's a lot of consequence to passing or failing specifications. And some of these rules are pretty much right at our limit of detection or very close to it, which says it's really important that we have these concepts be well defined. So, what is the detection limit meant to accomplish? Common applications, specifications, environmental regulations and limits, data reporting. It might be an SQC or SPC, required figure of merit. And sometimes, perhaps too frequently, they're used for data censoring, and we'll talk more to that point later in the talk. So what does a detection limit represent? Excuse me while I get a drink of my coffee. It's the lowest result, which we can trust in some manner. We'll try to make that manner be a statistical manner. It's the smallest amount that has a low probability of being due to noise, or it's the smallest amount that can be reliably detected. The latter of these is the Curie approach to detection limits. The former is things like such as the EPA definition philosophically are doing the first part of this point. They're a measure of a specific aspect of the capability of a measurement method or part of a measurement method. They're a figure of merit, and they're a mathematical and statistical construct. There are many acronyms: instrument detection limit, lower detectable limit, limit of quantification, minimum reporting level, practical quantification limit, limit of guaranteed detection. And there are many alternative definitions that are available for each of these concepts. And a quote from the ASTM Conference on Detection Limits in 2016, which I particularly liked: even within the same environmental agency, when offices are tasked with similar activity, the definition for detection limit will have a different meaning dependent on the office that defines the term. Even up and down the same hallway, we cannot get agreement on detection limits. The American Chemical Society, ACS, they provided something that's useful, but it also has some limitations. They gave sort of a size hierarchy to go with some of these conceptual categories of detection limit definitions. And this comes from the Reagent Chemicals Specifications and Procedures 10th edition, that the ideal detection limit or instrument detection limit is going to be less than the lower limit of detection, which will be less than the method detection limit, which will be less than the limit of quantification. But interestingly enough, if we actually quantify these things, this ordering may not always happen in practice. And it happens because of inconsistencies in terms of which error sources are used in each definition. There's sometimes inconsistencies within these classes of definitions. And this ordering doesn't account for that randomness when definitions are too similarly behaved for the system in question, and ICP methodologies. Some of these limits, you'll get limits that are very close to one another, despite calling them by different names, simply due to the nature of how the instrument behaves at very low levels of quantification. ACS even goes beyond just ordering these concepts. They provide a set of expected ratios that the limit of quantitation is likely to be 10 times the instrument detection limit, and the MDL is in the ratio of 4 compared to 10. But these ratios, you could find these claims elsewhere that are published. They can be thought of as relatively rough rules of thumb, but they may not be applicable to your particular measurement system. And they're not really exact rules. They're just sort of they have a utility, but you should not expect them to be very exact things. In general, good MDL practices are going to depend on the nature of the measurement system and the procedure. And there really is no one-size-fits-all detection limit definition that's going to make everybody happy. So you should expect that there will be more than one, but we need to define detection limit concepts that are useful for our intended purpose or practice, whatever that may be. A excellent quote in the ACS discussion: detection limits are controversial principally because of inadequate definition and confusion of terms. And this situation remains true to the present. The definitions are often confused with one another in practice. ACS liked a particular definition, the semi-C10 definition, which they said is more relevant for trace and ultra-trace metal impurity measurements. That's because it was specifically developed for trace and ultra-trace metal purity measurements. I shared that particular effort, and actually the author of the ACS book, the editor, was also involved in that effort, and it was, an active contributor to it. But what are some of the distinguishing characteristics of different detection limit methods? So if we sort of look at the IDL instrument detection method, it's going to be typically defined as a concentration that produces a blank signal equivalent to at least 3 standard deviations of the blank. So think of that, the 3 standard deviations is coming right out of normal theory. Another definition, which of course is going to give you a different limit, concentration that is equivalent to 5 times the noise in the signal to noise ratio. And ACS did not note it, but others sometimes use 2, 3, or 10 times signal to noise for IDL definition. So there's a great inconsistency in practice out there. In fact, when someone provides a detection limit to you, the first question you need to ask them is, which definition did you use? And then did you even use a particular variant of that definition or not? Because otherwise you don't even know what the detection limit means that's been handed to you. It's analogous to the situation where someone gives you a plus or minus. Is it plus or minus 1 standard deviation, 2 standard deviations, 3 standard deviations? Is it plus or minus half the range. What have they given you? Is it a 90% confidence limit? Is it a 95% confidence limit? So detection limits, just like statistical uncertainty, if you don't ask what you've been provided, you simply do not know. ACS did note that sometimes it's impossible to obtain a blank measurement. So different analysts in general could get substantially different instrument detection limits, but this will be true for every version of detection limit. Every definition has multiple versions of the definition, and practice can differ. So there's a great deal of inconsistency out there. Another concept ACS defines is the lower limit of detection, and this is the concentration such that 99% of the samples with this concentration will produce a measurable signal. This also has sometimes been called the limit of guaranteed detection. It's also the same as Curie's LD, which is a version, basically another version of the lower limit of detection. Others may choose to use different confidence limits in their definitions, but 99% is fairly commonly used with this particular class of definition. The ACS definition, as do many other definitions, they actually rely on large sample normal theory and does not correct for sample size, which leads us to an overestimation of confidence, because we frequently use a small number of measurements to actually obtain detection limits. And ACS also provided something that controlled a variety of errors, but their definition did not do so. So they included something that I guess that didn't fit. But it was a well-written discussion. It's 2 pages, a brilliantly written 2 pages. It's a very ambitious overview, and even just to have a fully described detection limit procedure, that by itself can span multiple pages. Okay, another key concept, method detection limit. So essentially, in the ACS version, you're going to measure a sample roughly estimated to be the MDL. You can see there's sort of an iterative issue in doing it this way, at least. And they want it to be at least measured at least 7 times and obtain the standard deviation. And a t-statistic at the 99% confidence level times the standard deviation converts the result into units of concentration. And this particular method detection limit, and the reason it has the word method there, is they're running the samples through the entire analytical method, unlike prior definitions, which do not include all the variability within the method. And 2 other key differences from the instrument detection limit: they're not using 3 sigma in theirs, they're using 99%. You're going to see there's often different statistical multipliers used depending who writes the definition. And the 99% in the MDL, this is not really the same as Curie's LD in the lower limit of detection. It's not guaranteeing a 99% detection rate. It's simply saying there's at most a 1% chance that a 0 could result in an MDL detectable signal. Limit of quantification. They did not explicitly define it in the ACS discussion, but often this is people will use a 10 standard deviation definition in practice. And the question is what sigma, what standard deviation do you use? And the whole business of the 10, it's really a rough statistical fudge factor that you're hoping covers all the hidden sources of error that did not get into the estimate of the standard deviation, or simply, that the quality with which you estimated the standard deviation is somehow covered for by a factor of 10. But still, even a definition like this, most of these definitions are in reference to a particular lab rather than being a global kind of concept. The practical quantification limit, the PQL, again, it's said to be about 5 times the MDL. You could define it that way. If you define it that way, then it actually is. And it's intended to accommodate the differences in detection limits that occur from lab to lab. So a company that's purchasing products from multiple suppliers, they might have a practical quantification limit that's meant to accommodate the differences that occur from lab to lab. But it still suffers from the fact that it really depends strongly on which lab the MDL you multiplied by 5 came from. And of course, you could quantify that in that expected ratio business. But as I said, look at these ratios very crudely. It has a limited value. Don't expect them to fall very precisely in those ratios. It will not happen. So we're going to take a break shortly for a few questions, but when I start after the break, we're going to talk about looking at a few concepts explicitly: signal to noise, the definition that came out of IUPAC. We're going to look at Foley-Dorsey's propagation of errors approach to detection limits. We'll take a look at SEMI C10, the guide for determination of detection limits. And we're going to look at the American Chemical Society EPA limits and Curie's view of detection limits. So at this point, we'll pause for a few questions and answers to try to make the talk be more interactive as we proceed. Okay, the earliest attempted definition of detection limit relied on instrument signal versus instrument noise, signal to noise definitions. And the idea would be that in this particular instrument, the large peak corresponds to something of interest that needs to be quantified, that's related to the signal scale. And near to that peak, the noise is quantified, the background noise, and then a statistical multiplier. And that multiplier, 3 and 5 are often used. Some have used numbers as low as 2 and even had the courage to publish that. But 2, 5, or 10 is applied to the noise for detection limit estimation. And this is perhaps, as I said, the oldest detection limit method, and it often provides very low detection limits. Instrument manufacturers love it. Contract labs love it because they could claim an incredibly low detection limit, but there's been a lot of pushback over the years against it as being too narrow a definition, that it doesn't reflect all the variability in a measurement method, and more advanced concepts or things that account for more sources of error or noise have been defined over the years. So if we look again at sort of the signal to noise, they're in reference to a single measurement, because that noise was within a single measurement, and that may not be the same from measurement to measurement, depending on what the instrument has seen recently. Linearity through the origin is implicitly assumed, and the noise is assumed to be independent of the concentration. And signal to noise allows gross extrapolation, that you may predict a detection limit that is 100 or 1,000 times less than the level you are measuring and estimating that limit. So it's partly, that's another one of the reasons it's dangerous, is it's frequently extrapolated orders of magnitude down from what is being measured. IUPAC, in their pre-1997 version of detection limit definition, they had a simple definition. They came up with something much more complex in 97, but they basically said, oh, we're going to measure the signal distribution of a blank. And of course, this presumes that the blank is even measurable. I drew a normal distribution over it, to pretend if it were normally distributed at the intercept. And then basically you're taking a signal that's the intercept plus 3 standard deviations and translating that back through the calibration model to come up with a concentration that is your limit of detection. There were some variants published to it. Instead of using 3 times the standard deviation of the blank, they basically, some used a t-statistic to correct for sample size, since very often a small number of measurements. They had actually said they required, supposedly at that time, greater 20 blanks, minimum of 20 blank determinations. But in normal practice, few ever collected the 20. The statistician said, well, maybe we could live with 20 and use the multiplier of 3. And using the t-statistic would correct for small sample size. But literally, if you put n equals 7 in there to have a risk-adjusted definition, that multiplier would have been 4.9 instead of 3. Foley-Dorsey came up with a propagation of errors approach to detection limits. And what they were doing is they were putting the error of the calibration line into, you'll notice in the equation they're using the standard deviation of the intercept, the standard deviation of the slope, as well as the standard deviation of the blank. So what they did is they accounted for the variability of the blank, but they also accounted for the uncertainty in calibration. And a variant of this would be, again, to replace the 3 with a t-statistic when you're using small n. And this was the earliest attempt at adding calibration error into an estimation of a detection limit. You could sort of say it was the first MDL, method detection limit effort. It assumes, this equation assumes a linear calibration model with an intercept. It assumes that ordinary least squares, that the error is the same everywhere across the calibration curve is the correct error model. And this propagation of errors, interestingly enough, is an approximation. It's not exact, but it works reasonably well enough most of the time, although you could define some circumstances that all approximations can be broken somewhere. The semi-C10 standard really is an exact version of the Foley-Dorsey propagation of errors. And it also allows nonlinear calibration, where you can define, you don't have to have a linear calibration to define a detection limit. And it allows weighted least squares if the error is not the same everywhere about the calibration model. I'll talk much more about the impact of heterogeneity of variance or unequal variance across the range of calibration later. So semi-C10 conceptually is looking at the calibration curve. It's building an upper confidence limit. You may or may not have taken measurements at 0. It's building an upper confidence limit for the uncertainty at 0, and then translating that back into the method detection limit. The American Chemical Society, MDL, simply looks, you'll see that this is basically looks somewhat analogous to the EPA definition, but we can see a little bit of difference here. We'll talk about that in a minute. It uses a t-statistic times the standard deviation of the sample signal, measured at least 7 times, and it's dividing by the slope of the calibration curve. In other words, it's translating it back. It's taking the signal variability and translating it back into concentration. And there's a 1% chance that a sample without the component of interest present will provide a signal at or above the method detection limit. And they did make the recommendation that the semi C10 definition was preferable to that definition for ultra trace measurement. Okay, the EPA, they're the ones who dictate. You're chatting with the EPA, you use their detection limit. You don't use any other definition. They have force of law, or at least regulatory law. And in 1984, in their appendix B to part 136, they defined the method detection limit as a t-statistic times the standard deviation in units of concentration. Often they required a minimum of 7 times, which translates into almost nobody measures more than 7 times. And it's using a 1% tail probability or a 99% confidence limit. So basically the ACS is analogous to this, the simpler definition that I had just shown. The replicate analysis, though, is performed on a sample with analyte in the range of 1 times to 5 times the MDL. And this is sort of because you don't really have homogeneity of variance down at the low level. Very often there's an iterative detection limit fishing expedition that takes place because you quantify it and you find you're not in the range of 1 times to 5 times the MDL. So it can be an iterative contest to get tame the numbers to behave with that additional requirement that EPA has. And 1% is the target chance that a sample doesn't provide a detectable signal. And this business, if we imagine that typically variation is increasing with increased concentration, even though our relative standard deviation is smaller, we frequently get higher signaled. So our MDL can become lower and lower unless we have a analyte that's already close. There's sort of a contest that the MDL you get can depend on the level that you picked. Okay, so in the imaginary world of variance homogeneity, there are 3 distributions that are drawn here. One is a distribution about the blank. We're trying to measure 0. On many instruments, blanks are measurable, but not on all instruments. If you're attempting to measure a true blank with a GC, for example, there's no peak to quantify. So there are cases where measuring a blank is simply infeasible. So the idea is that EPA, you measure a sample, and you'll note that the tail of the distribution, the left side of that green curve, essentially is crossing 0 with only a little bit of the curve is to the left of 0 that that if I get a signal at that level, I'm pretty sure I'm above 0. And Curie took the detection limit approach of saying, whatever I claim is the detection limit, that green line in the middle, vertical line, that there's only a small chance that I detect that I measure something as low as that if I'm at the level that he's showing. That basically, he's basically trying to guarantee, in that approach, you're basically trying to guarantee that you'll at least, that if you have a signal at that level, it will be regarded as detectable most of the time as compared to that lesser form of detection limit. So in general, Curie's detection limit is going to be larger than essentially the detection limit that simply says, does it stand out above 0? And I'll equate this to religion because these concepts are often fought about in practice with the ferocity of almost religious camps. But what I'll tell you is those are being regulated, like the detection limit number, to be a higher number. And the regulators like the detection limit to be lower to not leave as much wiggle room. I'll call that mean green. But what I will say is the regulated can't survive definitions like the EPA definition whenever you put the detection limit, whenever the detection limits are in the neighborhood of the regulatory limits. As detection limits and regulatory limits come together, there's a ugly clash of the fact that you're going to have violations due to chance rather than actually truly having a physical violation of a regulatory limit. And this big picture becomes a lot more complicated if there's variance heterogeneity. What variance heterogeneity means is in this picture, each of those three curves, the black, the green, and the blue one, were drawn with equal width or equal scatter. But frequently, most commonly with trace contamination measurements, whatever the distribution of the blank is, let's pretend that is the correct distribution of the blank, the right width. When I measure the sample in green, that's going to be wider, potentially much wider than the sample distribution I had for the blank. And then at the highest level, the blue distribution would be even wider than the green distribution, than the black distribution. So with variance heterogeneity, we have a much more complicated picture, and things don't quite line up as prettily as they do in that picture. So Curie, the detection limit is not a detection limit. He just calls it the critical level, LC, signal level above which the observed instrument response can be reliably recognized as detected. LD, the detection limit, it's the true net signal level that we could expect that will lead to detection. And limit of quantitation, the determination above which the quantitative measurement can be performed with a stated relative uncertainty. And he was very philosophical. He kept asking the fundamental question, what do we mean by a detection limit? And this is something that we always need to keep asking. He had numerous detection limit publications and awards. He was a NIST fellow. A lovely quote you can find out on the internet as well as in publications. Until Lloyd Curry's 1968 paper, Limits for Qualitative Detection and Quantitative Determination, Application to Radiochemistry, was published, there was enough inconsistency in the definition of detection limit to conceal a great deal of disagreement. By the way, that statement is still true today, unfortunately. Even though Lloyd helped out, it didn't get enough alignment in the end. Just over 7 pages, a high level of uniformity, fundamental information, influential far beyond its size. It's still discussed, nearly 50 years later. It's one of the most cited publications in analytical chemistry. I checked at one point it had 4,413. It's probably several hundred higher by now. And then this author in their very next sentence describes their own detection limit notational deviations from how Curie did it. And what I would say is the detection limit problem is a very worthy opponent. So what do all detection limits have in common is that we ultimately have some version of statistical uncertainty that's passed through calibration. So that sort of the green up and down arrow on the left side is some measure of statistical uncertainty over and above the average expectation, which is the calibration line that's drawn there. And we come over to the calibration line and we estimate the detection limit by having that green statistical uncertainty. And that uncertainty could have one or more sources of variation depending on the definition. And, we're almost always using 2 points from the calibration model. we're frequently using both the intercept commonly, and then we're also using the point at which that signal passes through. Another thing that detection limit forms have in common is that they're using some statistically scaled, typically 3, maybe a t-statistic, estimate of variation through calibration. So how good is, if we had 7 blank measurements or 7 measurements of a sample, we have 6 degrees of freedom. This table basically says how relatively precisely a standard deviation may be pinned down. So looking at that yellow line, if I wanted to sort of say like, well, if I were looking at the 95% confidence limits on the standard deviation, and imagine hypothetically that I estimated 1, because it's going to be a relative measure, it's saying the lower limit, it might be 0.64 of what I estimated, 0.64 of 1, or it might be 2.2 times greater than what I estimated. So literally, the standard deviation, you could sort of say, has a range of, from, it could be triple its lowest value in that confidence limit, more than twice what we measured, and as low as 64% of what we measured. So a standard deviation does not settle down very quickly as a function of sample size. And what does this mean? So if we had, if I took the EPA MDL definition, assume that the calibration error was irrelevant, okay, which that definition does anyway, and the true MDL was 1. So think of it as I simulated the MDL estimation process, I made the true MDL be 1, and then I said, what happens if I do use 7 measurements following the EPA quantification rules? I do get my average of 1, but how precise is that 1 pinned down when n equals 7? My standard deviation is 0.3. It's a skewed distribution. You can see it's longer tailed on the right. The relative standard deviation with which we estimate, 0.3 divided by 1, standard deviation divided by the mean, we're estimating EPA detection limits, assuming everything else is working, with a relative standard deviation of 30%. So there's high relative uncertainty and there's asymmetry involved as well too. And you can see that estimates as low as 0.3 were derived and as high as, for example, 2 and even somewhat above were derived as well. Okay, well, what kind of risk do we have in some sense of that we might, that 1%, we tried to define something where we had 1% risk of essentially a false detect. What actually happens? How does that risk vary? And what's interesting is that 77.3% of the time the risk is less than 1%. So that's good. So 3/4 of the time our risk was less than 1%, but the 90th percentile of risk, 10% of the time, actually we have almost a 3% chance that we'll get a false detect. 5% of the time we'll end up with an MDL that gives us a 5% chance of a false detect. And 1% of the time we'll have a 11.5% risk. So in a certain sense, we've not pinned the detection limit down very well in relative terms with such a definition. In general, the usefulness of a detection limit definition, what's its intended use? How do people actually use it? What are the consequences of the risks that the detection limit builds in? How many detection limits are simultaneously relevant? If you have to meet 20 or 30 different detection limits for different trace contaminants, your situation is much more complex than if you only have to deal with one. So what might work well for one detection limit may be trash for many. And we're going to talk about how we could sort of mess up a detection limit definition. And there are going to be 2 primary ways that we could accomplish that. One is we could misplace that brown line. where should the calibration line be? And the other capability of messing things up is if we misspecify the statistical uncertainty, because it's these two in combination with each other that lead to the detection limit estimate. So calibration is underappreciated in many detection limit rule sets. And I'm going to basically make the claim that no detection limit definition will survive or fully survive inappropriate calibration. So we're going to look at calibration from two standpoints: when we inherently misspecify the calibration model, or if we have an inappropriate model fitting process that causes misspecification of calibration. And it's time to pause for a second discussion break, again, in the hopes that we could interactively deal with some of the questions closer to the point where they were in your minds. All right, so before the break, we had sort of started with the issue of calibration. What are some calibration model forms that are common? The most common models are linear models, perhaps the line through the origin, or more frequently a line with an intercept. And most detection limit methodologies just assume that calibration is linear. Instrument manufacturers work very hard to achieve linearity of scale, but all models aren't necessarily linear. Sometimes there are nonlinear models that are not in a polynomial form. Sometimes second and higher order polynomials are used for calibration as well. Calibration can become messy when there are what are called matrix effects. Essentially, there are multiple things in the matrix, and they affect measurement of each other. The simplest correction is called the method of standard addition, and if that's not enough, full correction actually requires multivariate standards and calibration. The only thing I want to point out here is really that if we choose the wrong calibration model choice, because we're basically taking that signal back through the calibration model, we're going to end up with an incorrect DL. Wrong model, wrong detection limit. And standard addition can be tricky when you're doing detection limit estimation as well. So, additional note. All right. So another possibility is that we somehow do something wrong in the model fitting process, and that we end up misspecifying the calibration model. So we're going to look at a very simple situation that occurs with high frequency and trace contamination measurement. Suppose we have a true calibration model is aligned with an intercept. So, very common, scenario for ICP, for example. And I'm going to say simply estimating the slope and the intercept can misspecify calibration. So, how can this happen? How often does it happen? And can this actually impact an estimated detection limit? All right, so let's look at that table down below. And it basically shows 6 standards were measured multiple times each. It shows the instrument's average count, and it shows the standard deviation of that instrument count. So the average count was 118 when the parts per billion was 0. The blank was 118. The standard deviation of that count was 34. But yet when my parts per billion were 20, I'm measuring, 300, roughly 40,000, and my standard deviation is 1,500, which is many, many times larger. You'll note that literally there's an increasing standard deviation with higher part per billion levels. Ordinary least squares fits calibration, pretending the error is the same at 0, at 1, at 2, at 5, at 10. Well, how does this impact essentially calibration? So we're going to look at it in sort of three different tables here. The leftmost table, detection limit quantified using ordinary least squares. And you'll note that those detection limits all seem to be floating in the neighborhood of 1 part per billion, roughly. But you'll notice that if weighted least squares was used for calibration, detection limits were substantially lower, literally orders of magnitude better than perceived by projecting the larger errors at the higher concentrations down to the lower level. So it has a lot of impact on detection limit quantification. But what about on the calibration curve itself? How did it show up there? Well, it has a lot of impact on the intercept. The ordinary least squares, variance, homogeneity, variability is the same everywhere model. It gave actually negative intercepts in 5 out of 6 of these trace metals. And one time it gave an intercept that was close to 1,000. But you'll notice that the weighted least squares intercepts tend to be very close to 0. The calibration model does pass close to an intercept of 0. Not exactly. There's like a small positive result, likely to be the fact that, blanks are not quite blanks, even though we try to make them be as close to a blank as possible. But essentially, much better behaved intercepts. And there's not much difference in the slopes between these two different kinds of fits. So performing calibration with the correct calibration model, linear model was fit in every case. But if we fit it the wrong way, which is the standard way Excel does it, the standard way a statistics package does it, you have to specify weighted least squares, and that takes extra effort, and most do not do that. Will literally destroy the validity of the estimated method detection limits and misplaces the location of the intercept substantially, which obviously is going to distort the entire business of where the MDL is located and found. This scenario is common in trace metal analysis. Okay. This table, there are basically two things shown here. One is showing the intercepts for basically 40-some trace metals by ordinary least squares, which are the squares, and the diamonds are showing via weighted least squares. And you'll see the interesting thing that happens, and that they were actually, you could see when they were actually present. If you look around the line at about 1,000 on this figure, heading across, you'll see that the same intercepts were obtained for those particular things. That things that were above the background, the intercepts tended to be very similar. But things that basically were not present, the ones where the weighted least squares intercepts were close to 0, the intercepts for ordinary least squares were all over the map and frequently were negative and biased. There was a systematic misplacement of the intercept. In all these models, the data, if you looked at things close to 0, the intercept should be close to 0, not far from 0. So this is why there was a major impact of misplacement in the intercept. If I were to show you the same type of figure for slopes, it would have looked very similar. So now we're going to move on to the whole business of how do we come up with a detection limit standards that fit, because most that are defined out there have some serious weakness to them. So basically, we have to look at what are all the intended usages along with the purpose of the standard. Frequently, people try to write standards without explicitly agreeing on the purpose of the standard and what the standard is to be used for. There are common unintended detection limit usages, such as censoring and other misuse. The definition of a standard should legislate what you should do with the detection limit usage as well to prevent misuse of the standard definition. What are the data structure requirements and the minimum sample size? Do we need to check something about the statistics that data we have is suitable for use with the model? What are the alternatives? Are they described? The model must be flexible enough to allow common alternative requirements to be incorporated. That was the idea in the SEMI definition. Hey, if you have multivariate calibration, the definition works. If you have nonlinear calibration, the definition works. It didn't just rely on linear calibration. But the idea of building flexibility allows routine situations to be handled transparently rather than a incorrect result being generated because the standard did not handle. What data adjustments are allowed or not? How do we prevent or limit extrapolated detection limits, that we can't collect data at a high level and pretend that we know the detection limit at a very low level? Is there a background problem or issue? How do we address that? And data reporting practices, they are in transition, but one of the things that commonly happens is detection limits are often rounded up. You calculate a value, but you calculate the detection limit as 1.32. What do? Very few report 1.32. You might report 1.5. You might report 2. They're frequently rounded up. By how much? What's the impact of that rounding? Have you ever seen a non-rounded detection limit? Should data be censored to detection limits? This practice is weakening, and correctly so. I am in the midst of reviewing a paper in Environmental Science and Technology that broadly reports on what happens if you censor to detection limits, what happens if you don't. There have been many papers written on it, but it's a systematic view. It's probably coming out in somewhere in perhaps the next 6 months or so. Paper's in its final stage of review. These subjects are mostly beyond the scope of this presentation. And, focus on what's actually done, not what is supposed to have been done. I'm sorry, I triggered moving too many slides. So the most common thing that happens with detection limit application is censoring to the detection limit. Most detection limit definitions do not say to do this. It seems to be commonly accepted practice if you do say that to do it. But what are the consequences of censoring? Well, there's some rewards if you censor the data. You have a whole lot less explaining to do. The detection limit, at least in years past for suppliers, it became sort of like a magic carpet that covers up some or much of the data that you didn't want to have to discuss with the customer. It also allowed visible calibration issues to be systematically masked in some situations. And it also makes data appear to be less variable than it is because, hey, data by the detection limit is inherently highly relatively variable. But there's some penalties for censoring. And basically, all statistical analysis of data is corrupted or greatly weakened. You could do fancy mathematics to try to recover. That coming paper in Environmental Science and Technology uses many different advanced methods, but none of them are as good as not censoring the data in the first place. Control charting, you'll have excessive false out of control signals because you made the data look less variable, which corrupted the control limit calculations. And data issues, if any, can be systematically masked, which is really not a good thing. Well, what if you don't censor the data? Well, not censoring the data, there are a series of rewards. You're going to be able to do unbiased statistical analysis, is often still feasible. Statistics doesn't care about how much variability is in the data, or how much relative variability. It can analyze the data at any level of variation. We are able to detect calibration issues, and we could detect systematic data patterns that are below the detection limit. The detection limit is not a magic point where the data ceases to be useful. It's simply not as useful as data that's measured more precisely. Well, what penalties if we don't censor to the data? Well, we need to look at statistical results more carefully, and it's really not a penalty. It simply says each data point by itself isn't quite as value, but clusters of data points can still be telling us something useful. we have risk of overinterpretation that rises. We need to educate where or when, a softer interpretation of the data is still useful. And then we might also have the pleasure of explaining negative results. Analytical systems could provide negative estimates of concentration. Frequently, they're censored to zero. That censoring is counterproductive, in part because if we do that censoring, it hides the essentially the fact that we may or may not have a well-calibrated system, but it's really tough to explain a negative value to someone as well. So there are both pros and cons with something like reporting a negative result. Okay, but the overall consequences of using a detection limit or zero for data censoring are ultimately worse than the consequences of not doing so, and that acceptance is starting to evolve. Okay, but it's not fully there yet. Okay, so once upon a time, we measured detection limits infrequently. Well, we measured them 5 years ago. Maybe it's time to measure them again. Then they're measured annually. Then they're measured quarterly. Then they're measured monthly. Sometimes they're measured almost every day in some systems now. So we sometimes now have large collections of the same detection limit being estimated sometimes. So how should we handle multiple estimates? And that's often missing in the detection limit standards. How should we use multiple detection limit determinations? Should we report an average? Should we report an upper confidence limit? And those are other types of issues that a standard may need to include. So basically, before you start detection limit standard construction, what are your scope, goals, application, context? What are all the sources of variation that are needed to meet your goal that have to be incorporated? What measurement method or methodologies will it apply to? If the answer is all, you have to stop because you'll never get a definition that you'll not get a one size fits all. You're wasting everyone's time. What should you be confident of? How confident? What is the maximum amount of data that's worth collecting? What's the minimum amount that's reasonable to collect? What are the essential ground rules? That, maybe like the detection limit must be less than the specification or regulatory limit. By how much, perhaps? The detection limit needs to be measured in the sample matrix or what? The statistical methodology is actually not even considered yet. That comes later. The statistical methodology has to fit all these things, not have all these things forced into the statistical methodology. What are the candidate statistical methods? What are the metrics for their performance? Have a contest between the alternative statistical approaches. Which one works best for what you're doing? Make the participating statistically literate contributors aim at the target, not provide a definition that they happen to like that may not fit the target. Define performance metrics to test the methodology. Consider whatever those participating consider useful as candidate definitions or pay the price. Performance metrics will take out any trash methods. Data and detection limit, there should be like an iteration. Look at how these different methods work. Look at what's working, what's not working. Iterate, and you're likely to end up with a methodology that's suitable for the intended purpose. And you have to document your decision path to the definition. Otherwise, you'll rehear all arguments in ballot and even within the meetings themselves. So you'll have detection limit definitions are constantly a new set of people arriving to the room, and you have to circumvent that in part by establishing what is already firmly resolved so that there's a higher threshold they have to overcome to raise the questions that you've already seemingly answered before. Okay, if you have, just like with trace contamination measurement, if you have any sloppiness in constructing a detection limit definition, it's going to be fatal. It has to apply to everything. There is no one size fit all. The lengthiest construction phase is defining and agreeing on what purpose the detection limit is intended to serve and its scope of application. Once you've defined that, you can move on. If you haven't defined that, every definition is premature. Standards can't be prescriptive in unrealistic ways, like forcing linear calibration where it doesn't apply would be an example. Standards have to reflect the approximate statistics the standard has to reflect the approximate data characteristics in the methodology. Time variation and detection limits might have impact on methodology. And what I'll call, the grandfather clause, or, granddad's superpowers for resisting detection limit change must be dealt with. So the prime granddad you have to deal with is the existing EPA detection limit standard, or whatever standard you intend to replace. You better document very well why it's not sufficient and why the new approach is better. Otherwise, you will still be using granddad 10 or 20 years from now. So psychological perception can be a limitation. We like one size fits all, makes life easy and simple. We want to simplify the computation, often oversimplifying. We often fail to question statistical models we already know. We often fail to fully question the detection limit models we already know. We think detection limit problems sometimes can be solved safely without data. And we need to question everything we think we know about detection limits with respect to our problem setting. There is a particular detection limit nightmare that occurs, and detection limit estimates are not always time stable. So in slide 34, we saw there was a 30% relative standard deviation in the EPA definition. I'm not talking about that uncertainty, but uncertainty that's even much larger than that. So this time instability, you could have a well-controlled trace measurement system, but you could see unusually large variation. And this undermines many definitions and points out that you might have to really be estimating detection limits multiple times, and perhaps even using a higher percentile than just the average detection limit in that. There's a talk which is also in the STP 1618 from ASTM that deals with how do you handle multiple detection limit estimates, what statistical estimates should be reported when you have many limits. And there can be an incredible amount of time instability in a detection limit on the same analytical system measuring the same standards. If you don't collect these detection limits multiple times, you won't see that. So a parting visit to the big picture, looking at the different versions of detection limits, Curry's LC and LD, but very often that middle detection limit using essentially the EPA definition, we're very close to the detection limit. The regulatory limit and the detection limit are very close. There's trouble when any detection has regulatory meaning, the imprecision in defining our detection limit, or even if we're close, the detection limit is close to the regulatory limit. The way we do things currently is going to come back to bite those using those detection limit methodologies. And those that in some sense have already been punished by having quantified detection limits that are too low usually understand more about detection limit concepts by having suffered. But in summary, you have to have an intense focus on defining scope, because if you can't agree on scope, you're wasting your time defining a detection limit definition or trying to agree upon one. You need to use data from the real processes to refine or referee decisions as to what methodology is best. The measurement system with all its real warts and birthmarks must be integrated into the detection limit definition because, hey, that's reality. It's not pure statistical theory. It's what our systems, the type of data our systems really provide us with. You need to document every process step or pay later. And I'd say there's really a step 0 too. Is a detection limit approach best for your application needs, or are other quantitative measures, of quantifying precision and bias better? So even question, when is a detection limit concept best for the intended purpose, or when is some other measure of basically precision or bias better? And papers from many of the 2018 MDL conference presentations, as I said, are in ASTM STP 1618. And thank you very much for attending, and I'm open for any and all questions once again.